Assalamualaikum warahmatullahi wabarakatuh, and hi. Today, my group members and I will present about mini project B for the subject ECH31116 heat and mass transfer processes. First, I will introduce my group members. My name is Ramaki Hamdan with matrix number 200388, Nadira Shaira binti Salihah with matrix number 200392, Hani Rahazika binti Harun Nur Rashid with matrix number 200607, Nur Aina binti Jamil 201114, and lastly Nurul Azira binti Yasir with matrix number 203725. First, I will do introduction for this project. Heat exchanger. Heat exchanger is a device used to transfer thermal energy, which is enthalpy. Usually, there is no external heat or and work interaction when the heat exchanger is in process. Heat is transfer between fluids takes place through a separating wall in a transition manner in most heat exchangers. Typical application for heat exchanger is for cooling or heating or cooling of fluids. Common examples for heat exchanger are shell and tube exchangers, automatic radiators, condenser, and evaporators. In this presentation, my group members will further discuss about the problem solving, project design, and also the conclusion for this mini project. Next, I will pass to the next presenter to continue the presentation.
Assalamualaikum. My name is Nur Aina binti Jamil and my metric number is 201114. So I'm going to present to you guys about our problem solving, which is our calculation. From the question given, we can get the properties of the water at the temperature of 25 degrees C from table A9. So the specific heat of the water is 4180. The dynamic viscosity of the water is 0.89 Y times 10 to the power of -3. The density is 997. The thermal conductivity is 0.607 and the prime number is 6.14. And from the question also, we made some assumptions. The first one is there is no thermal resistance, so the R wall is equals to 0. And the heat exchanger is well insulated, so the rate of heat transfer of the hot water is same as the rate of heat transfer of cold water. The tube is thin, so the thickness is negligible. The surface area for inner and outer surface is the same. The overall heat transfer coefficient is constant. There are some data given, which is the first one is total number of the tubes is equal to 40. The average shell side heat transfer coefficient is 2994 watt per meter squared K. The mass flow rate of the cold water is 18,000 kg per hour, which is equivalent to 5 kg per second. And the mass flow rate of the hot water is 14,000 kg per hour, which is equivalent to 3.89 kg per second. And the inner diameter of the tube is 1.9 centimeter, which is equivalent to 0.019 meter. From the right side of the slide, these are the list of the equations that we use. This is the temperature change diagram for all design, since all design is a multipass. The first design is multipass, one shell pass and one tube passes counter flow. So from the surface area of the tube, length of the tube is equals to 4.57 meter, which is more than 2.5 meter. So this design of the heat exchanger is rejected. Our second design, which is a multipass, one shell pass and two tube passes parallel flow. We also calculated the length of the tube from the surface area of the tube, and we get the length of the tube to be 2.85 meter, which is also more than 2.5 meter. So this design of heat exchanger is also rejected. And for our third design, which is multipass, one shell pass and two tube passes counter flow, for this design, we get the length of the tube to be 2.29 meter, which is less than 2.5 meter. So this design of heat exchanger is accepted. A final design, which is a multipass, one shell pass and four tube passes counter flow. This one is actually the modified design of our third design, which is multipass, one shell pass and two tube passes counter flow. So the calculation for design third and final design is the same. So we only show the calculation for the final design. To calculate the average velocity, we substitute the value for the mass flow rate of the cold water, the density of the cold water, and the area, and we got the value of the average velocity is equivalent to 17.69 meter per second. And from average velocity, since the total number of the tubes is 40, we divide by 40 to get the average velocity for each tube, which is 0.442 meter per second. And to calculate the Reynolds number, we substitute the value for the density, which is 997, the velocity that we calculated just now, which is 0.442 meter per second, and the inner diameter of the tube, which is 0.019 meter, and we divide it by the dynamic viscosity, which is 0.891 times 10 to the power of negative 3, and we got the Reynolds number 9397.09. We also calculated the prime number. We substitute the value for dynamic viscosity, which is 0.891 times 10 to the power of negative 3, and we substitute the value for specific heat of the cold water, which is 4180, and we divide it by thermal conductivity, which is 0.607, and we got the prime number to be 6.14, the same like we got from table A9. Okay, so by following a Colburn equation, since the PR is within the 0.7 and 160, the flow is fully turbulent. So now to calculate the Nusselt number, since this is a turbulent flow, we use the formula of 0.023 times with the Reynolds number to the power of 0.8 times with the Prandtl number to the power of n. Since this is a heating process, so the n is equivalent to 0.4. So we just substitute the value of Reynolds number and Prandtl number, got the Nusselt number to be 71.68. To calculate the value of the heat transfer coefficient, we just substitute the value of the Nusselt number, the value of the thermal conductivity, and the inner diameter of the tube. Heat transfer coefficient is 2290. We first calculate the rate of heat transfer of cold water. So we just substitute the mass flow rate of the cold water, which is 5 kg per second, the specific heat of the cold water, which is 4.18 kilojoule per kgK, and the change in temperature for the cold water, which is the temperature of the cold water going out minus the temperature of cold water going in, which is 45 minus 25 degrees Celsius. And now we got the value of the rate of heat transfer of cold water to be 418 kilowatt. So since the rate of heat transfer of cold is same as the hot water, we just substitute the value of the rate of heat transfer to find the value of the temperature of hot water going out. Got the temperature of hot water going out to be 54.29 degrees Celsius. So to calculate the log mean temperature difference, we first calculated the delta T1, which is equivalent to temperature of hot water going in minus the temperature of cold water going out, which is 80 minus 45 degrees C, and we got 35 degrees Celsius. And we calculate also delta T2, which is the temperature of hot water going out minus the temperature of cold water going in, which is 44.29 minus 25 degrees Celsius, and we got it to be 29.29 degrees Celsius. So we substitute the value of delta T1 and delta T2 to the log mean temperature difference formulas. We got 32.06 degrees Celsius. To know the value of F, we calculate the P and R. The P is equals to 0.36 and R is equals to 1.29. And from the figure 1119, from the value of P and R, we get the value of F to be 0.92.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nadira Shahira binti Solehan and my matrix number is 200392. Okay, next we calculate the thermal resistance of the heat exchanger, which is 0.000771 m cubic Kelvin over watt. And then from that we can calculate the overall heat transfer coefficient, which is 1297.55 watt over m cubic Kelvin. Okay, since the surface area for inner and outer is the same, so we can calculate the surface area by using the rate of heat transfer equation. So the surface area that we get is 10.92 meter cubic. Since we follow the one shell and two tube passes of heat exchanger, so we divided the surface area into two, and each tube we will get 5.46 meter cubic of surface area. Then from that we calculate the length of tube is 2.29 meter. So as we can see, the length of the tube is below 2.5 meters, so the heat exchanger is accepted. But we have modified the heat exchanger from 2 tube passes to 4 tube passes counterflow by using the same length of tube. So the new surface area is 21.87 meter cube and the rate of heat transfer is 837 kilowatt. So the multi-pass, one shell pass and 4 tube passes heat exchanger was designed and chosen to heat up the water at the limitation space in the plant. The length of tube used is 2.29 meter, which is less than 2.5 meters. So it suit and fit in the narrow area. The heat exchanger was modified from multi-pass, one shell pass and 2 tube passes to multi-pass, one shell pass and 4 tube passes to increase the rate of heat transfer of the heat exchanger. This is because by increase the tube passes, the surface area of the tube will increase, so the heat will be transferred more faster. Okay, next, with the falling factor, the new temperature of cold water that flowing out is 42 degrees C because the temperature of cold water at the outer decreased by 3 degrees C. So we assume the outer temperature of hot water also change due to TCO change. So the new THO that we get is 58.15 degrees Celsius. So then we calculate the log mean temperature difference and we get 35.52 degrees Celsius. And then we calculate the P and R constant, which is 0.31 and 1.25 respectively, and the F value, which is the correction factor, this multi-pass is 0.95. So lastly, we calculate the falling factor by using the thermal resistance equation and we get the RF is 0.00000032 meter cubic Kelvin over watt. So the estimated falling factor is very small, which is 3.17 times 10 to the power negative 7 m squared K over W. Because it is water, the falling inside the tube will causing the surface roughness to increase and therefore will increase the frictional resistance to flow. So that's all from me. Thank you. I will pass the presentation to my friends.
Okay, my name is Hanina Zikaminta Harun Rashid, and next I'm going to present on the project design. And we have proposed 4 designs. The first design is one shell, one tube passes multi-pass, where the steam will move through the shell from the entrance and exit at the bottom and top of this heat exchanger, while the tube will be passed through by the cold water. For the first design, it will move just in a straight line. And then for the second design, it is one shell, one two tubes passes parallel flow, where the cold water will enter and make such a U-turn and went out from the same side. So these 2 designs were not accepted because from the calculation we found out that the length of tube is more than required. So we went to design 3 and 4, where the third design is a one shell, two tube passes counterflow. It's quite similar to the second design, except that the flow here is counterflow, while the second design use parallel flow. So next, from this we have modified the design into design 4, where we use one shell, 4 tube multi-pass. So the cold water will pass through the tube for 4 times. From here, 1, and then going 2, 3, and then 4. So this is a summary for our design. We have rejected design 1 and 2 because the tube length is more than 2.5 and accepted design 3 and 4. And all of this use counterflow except for design 2. And the number of tube passes is 1 in design 1, 2 in design 2 and 3, and 4 in design 4. So we have used AutoCAD to make our final design, which is following the pot design. And the grey colored one is the shell, while the red colored inside is the tube. And this is from the side view. You can see that the shell entrance and exit is here and here. Okay, and the dimension of the tube is stated here, 2.29 meter. Okay, next I'm going to pass to the next presenter.
My name is Nurul Natzira binti Yasir and my metric number is 203725. Let's take a look at the design improvement and modification. The reason why we choose design 4 as our final design is because from the calculation, the tube length that we get is 2.29 meter. This tube length is below 2.5 meter, so our design 4 can fit perfectly in the limited space of the plant. Some of the modification that we made in this design is we modify 2 tube passes in design 3, which is multi-pass 1 shell 2 tube passes counterflow to 4 tube passes. The reason why we add another 2 tube passes is to increase the surface area of our heat exchanger. By increasing the surface area of our heat exchanger, we can speed up the heat transfer reaction. Thus, we can increase the efficiency of our heat exchanger. Next, we add buffers on the shell side to direct the shell side feed to flow back and forth across the tube in order to create multi-pass effect. We also use a durable material, which is stainless steel, for our heat exchanger. Now, let's move on to fouling. What is foulings? Foulings are undesirable material that form on heat transfer surface. It can increase the heat transfer resistance and lead to poor performance of our heat exchanger. One of the causes of foulings is the presence of minerals in the water. This excessive amount of minerals can cause precipitation on our heat transfer surface. Next is the operating condition. If we operate our heat exchanger in a very high heat or in a very high velocity flow, it can increase the risk of foulings. Last but not least, the presence of microbes and other contaminants. For example, microbes can cause a slick film on our heat transfer surface. There are many ways to reduce foulings. One of it is by increasing the energy consumption, but this method is quite pricey. By increasing the energy consumption, our heat exchanger can perform at a very peak intensity, and it also can increase the water turbulence. We must select a durable material for our heat exchanger. We also must apply coating in order to reduce foulings. Fouling can also be reduced by performing regular cleanings and regular inspection of our heat exchanger. Last but not least, the most effective method to reduce fouling is by setting up a treatment system. We can cooperate with industrial treatment water services so that they can remove the undesirable substance and they can treat our water. That's all from.
In conclusion, design 4 is chosen as the final design. This is because the design specification is the most ideal in theoretically way, and the design also the most efficient to carry out the heat transfer process. That's all from us. Thank you.